Okay, so today we're going to enter a few lecture segment about property testing and PCPs and constraint satisfaction problems and hardness of approximation and similar topics. In particular, today we're going to talk about property testing functions, which we mentioned a little bit in lecture 2 when we talked about the Blum-Luby-Rubenfeld test for whether an unknown function was a linear function over f2 to the n. So if you remember, in the property testing model, roughly speaking, you have black box access to some function, and you can ask queries. You can give it some string x, and you'll get back out f of x. And you're trying to decide if this unknown function f that you have access to is in some class of functions C. Okay, so you have some fixed class of function C. You're trying to roughly decide if it's in this class C, or you can think of C as defining a property of Boolean functions. And you're trying to tell if f has this property. So in the most usual model of property testing, usually you allow yourself a large constant number of queries, let's say, and you want to have a very good opinion as to whether f is in C or not. But we're going to actually talk about an even more restrictive version of property testing where you really only allow yourself a tiny number of queries, like 2 or 3 or 4. And you have to make a somewhat good decision about whether f has C. OK, so let me make a couple of definitions that we'll need for the next few lectures. And the first one will just be our definition of what a property testing algorithm is. And there's a few variants that you could imagine here. So I make this definition so that we can fix on some conventions. So we'll say an R query function tester well, it's a randomized algorithm with black box access to some function f. Like over here. And it acts as follows. First, it chooses, let's say, up to R random strings inputs, which we'll call x superscript 1 through x superscript r. Perhaps there's less than r. Somehow. OK, so they don't have to be independent or anything. In fact, most likely, if you have a clever function testing algorithm, they'll be correlated somehow. But it's going to use its randomness to decide on up to r query strings. And then it queries on these strings. OK, and so it gets back r bits. And now, finally, it makes its decision on whether or not to accept f. OK, so, and I want to say that it decides deterministically. Something happened funny there. All right. Let's see if we can fix that. All right. I'm sure that'll really be edited out later. OK, nobody breathe now. Deterministically, let me continue over here, whether to accept or reject f, okay, based on the outcomes of the queries. OK, so this is the model we'll choose. One thing we notice we don't allow here, for reasons we'll see when we study CSP, is we don't allow adaptivity. So in this model, the tester uses its randomness to decide on the strings it wants to query, and then after that, it's deterministic. So it doesn't like make some queries, then decide what to do randomly next. OK. So that's what our algorithms can do. And now let's define what it means for an algorithm to be, let's say, a good testing algorithm for a class of functions C like this. OK, so here's another definition. Let C be a collection of functions, let's say from -1, 1 to the n into -1, 1. say a local tester for C so a local tester for C, is that really cued by the door opening? It's kind of awesome. Here, try opening that door again. I almost got attacked that time, too. All right. Or maybe somebody breathed too hard. I'm always nervous on this side of the room now. Right, so a local tester, where was I for C? Oh yeah, it has some parameter that we mostly don't talk about too much, but we need to say it in the definition. Oh shoot, someone's coming in. Oh man, what are you doing? This comes down, we're dead. All right, we're okay. It's fine. Come on in. All right. Great. Yeah, I better get to writing. With rejection rate lambda. Okay. This is some constant that is not super important, but we may as well write it. Is a tester of this sort with the following properties. First of all, if the function is in the class, the tester should always accept it. So if f is in the class, the tester accepts with probability 1. Okay, and as we saw in the BLR test, the converse is sort of a bit weaker than this. If, roughly speaking, if you want to say if the unknown function is far from every function with the property, then the tester has some good chance of rejecting, not accepting. So for all 0 less than or equal to epsilon less than or equal to 1, if the distance of f from the class is greater than epsilon. And here, I mean, this is like the minimum of the distance of f and g for g in the class. Okay, and remember the distance between two Boolean functions f and g is the fraction of inputs where they disagree. Then, finish this thing over here. Then the probability that the tester accepts should be less than 1 minus, well, let me write it like this. The probability that it rejects should be greater than lambda times epsilon. Okay, so think of lambda typically as, I don't know, some small but positive universal constant like 0.1 or something. Okay, so it actually says that the probability of rejecting is proportional to the distance from the class. And one could imagine some weaker requirements too here, like it's not clear why this probability should be linear. You could imagine maybe it rejects with probability epsilon squared or epsilon over log n or something. But for simplicity, again, we'll just assume that the probability is always at least proportional to the distance from the class. Okay, and it's sometimes good to think of this in the contrapositive. So if the tester accepts with probability at least 1 minus lambda times epsilon, then f is epsilon close to the class. Okay, epsilon close means the distance is at most epsilon. Okay, any questions about that? Okay, so one thing a small thing I want to point out from this definition, in particular, if you have a tester for a given class, then it satisfies both of these two properties. Say this is 1 and this is 2. And if you take epsilon to be 0 in 2, okay, so it actually has to, 2 has to hold with all epsilon, but in particular it has to hold with epsilon equals 0. What that means is if the distance is positive, so if the function is not in the class, then the tester has to reject with positive probability. Or reverse, if the tester accepts with probability 1, then you're actually in the class. So you get that combining it with 1, f is in the class if and only if the probability of acceptance by the tester is 1. It's pretty awesome. Damn you, Arda. I'll fill you in. So every time somebody touches the door, the screen goes down.
Really?
Yeah. Unless it's a Maya. Nobody leaves and block the door. It's like the most popular class, too. Usually there's not so many of you. Yeah, it's entertainment today. Okay, very frazzled. Yeah, so in particular, like a local testing algorithm, like characterizes functions in the class C. Like you're in the class if and only if the tester accepts you with probability 1. But more than that, it's like a robust characterization. Okay? Yeah, it's a bad name. I don't really like it. The local refers to the fact that, typically you make some R queries where R is like an absolute fixed constant. So it decides roughly if f is in the class by looking at its values locally on only a few input strings. So somehow I guess the name is motivated by locally testable codes, but it's not a great name.
I mean, in testing, is this the only model? The only query at this point and then?
Usually, the more usual model in property testing is that you think of having a parameter epsilon given to the algorithm. And if the distance from a function from the class is bigger than epsilon, it should reject with probability half or something.
That just makes the definition robust, right?
So this model, if you have such a thing, it's stronger. Because one thing you can do, let's say you make 5 queries and you have this property. Then if you're additionally given a parameter epsilon, you can run your algorithm. You can run your algorithm like 5, 1 over epsilon times. You'll make like 5 over epsilon queries. Maybe I'll just do the rest of this lecture without visual aids. I don't know if I can even make it go up anymore. What's going on?
Things on the wall for it?
I think this is for like. This one is for the Windows, I thought. No? Okay. We can try that too. I mean for the Windows shades. This is awesome. Anyway, you could run, if you have such a local tester, you could run it like 1 over epsilon times, and then you would check that if the function is epsilon far, you'll have like an absolute constant chance of rejecting. So then you'll make a number of queries that depends, in this case, linearly on 1 over epsilon. In the more traditional property testing model, you're just given epsilon, you try to make 1 over epsilon, polyeps, 1 over epsilon, exponential, and 1 over epsilon many queries to achieve this constant probability of rejection. So this is a pretty strong requirement. Yeah.
What is the somehow indicator?
Oh, it just me. All I'm saying is that this is where the smarts of the most of the smarts of the test algorithm designer comes in. You have a clever way of choosing x1 through xr.
Oh, so it's not just like uniformly.
Yeah. It's not just uniformly at random. Well, probably each will be uniformly at random, but they'll be correlated. Yeah, they definitely won't be independent usually. Okay, any more questions?
But aren't they independent without linearity testing?
No, so let me remind you about the linearity testing thing. This is like our most basic example of one of these local testers.
Oh, yeah, 2 of them are independent.
2 of them are independent, but the third one is not. Yeah, so here's an example. This is from lecture 2. It's called the BLR tests, Blum-Levy-Rubenfeld. Okay, and it's for the class of linear functions, F2 linear functions, although by now we're mostly happy with plus or minus 1 notation, so you might also think of it as the class of parity functions. For all subsets S. Okay, so it's a class of 2 to the n functions. And how did it work? It was a 3-query local tester. Query local tester. And how did it work? It chose x and y uniformly and independently. But then the third input, as Arda said, is not independent. It sort of sets z to be the string. It's like the pointwise product. So zi is xi, yi. And then it queries f of x, f of y, f of z, and it accepts if and only if f of x, f of y, f of z equals 1. Okay, so this is a test that will pass with probability 1 if it's really a parity, because this will all cancel out. And if you recall our analysis, it was like the very first sort of thing we did with Fourier analysis. You can write the probability that this will accept some function f as it was like a half plus 1/2 times the sum over all s of the Fourier coefficient of s cubed. That was an exact formula, and we also noted using Parseval that this is at least a half plus a half. You can take out one of the f hat s's with a max, and what remains is the sum of the squares, which is 1 by Parseval. So we have this. So why does that satisfy the two properties? Well, you can see directly from the test that if f is a parity, it passes or is accepted with probability 1. You can also see that from the Fourier formula from the probability of acceptance. In the case that f is in the class, one of these Fourier coefficients will be exactly 1. The rest will be 0, so you'll get, indeed, half plus a half times 1 is 1. So if f is in the class, it's indeed true that the probability of acceptance is 1. And conversely, if the probability of acceptance is at least 1 minus epsilon, then this thing has to at least be 1 minus epsilon, which means that there has to exist some s star such that f hat s star is at least 1 minus 2 epsilon. Okay, and this is the correlation of f with the parity parity on s star. So in turn, this implies that the distance of f from chi s star is at most epsilon. Okay, so in particular, this is a 3-query local tester with rejection rate, this lambda 1. Okay, because really this is like there's a, I could put a 1 times in here.
Is that supposed to be a less than or equal?
Where?
Bottom left.
Yeah. Thanks. Okay. Let me make an extremely pedantic comment now. Usually what's going on when you're talking about testers and testing Boolean functions like this is you actually have a sequence of collections of functions, like one for each n. Like here, like really you have the class of all parities on n inputs for various values of n. And technically you usually have like a separate, I mean, by definition you have a separate tester for each value of n. But generally in the examples it'll kind of be the same thing for all values of n, as it kind of was here. And the main point will be that this rejection rate is some absolute constant that does not depend on n. Okay, so I'll slightly blur this distinction between testing for a fixed n and testing for all n. It should never really cause any confusion. Okay, one other thing that
Brian,
yeah.
Sorry, so why is that lambda 1? I mean, I thought that the distance is like 1 minus 2 epsilon, right? Yeah. And the acceptance 1 minus epsilon. So, I mean, there you have like distance being more than epsilon, then
Yeah.
then the probability of rejection is at least lambda epsilon.
Yeah.
I'm just getting into this. Shouldn't lambda be half? I mean,
No, just, I mean, if you want, forget these two lines for a second. Here we have probability at least 1 minus epsilon implies distance is at most epsilon. Okay. All right. Let me make one more, while we're on the topic of BLR, let me remind you of one thing that we mentioned way back when. which will be useful to us later. It does not 100% directly relate to this local testing. But remember, we had this idea. Once you have some unknown function that's, let's say, supposed to be a parity, you can run this BLR test and perhaps become convinced that it is a parity. One thing that you might actually want to also do is like learn or be able to access the value of that parity which you're close to on your favorite string. So we defined this little algorithm called local correct, given access to f and a string x, that just does the following. Choose y uniformly at random, and output f of y times f of z, where z is this pointwise product of x and y. So this is like a two-query algorithm that doesn't output accept or reject. It actually outputs like a bit, like its guess at what f of x should be. And the little theorem that we proved about it, and please remember this for when we're going to apply it. We proved that suppose f is epsilon close to some parity chi s star, then for all x, the probability that running this local correction algorithm on f and x, that this equals chi s star of x, is at least 1 minus 2 epsilon. Okay, so if you somehow know that f is indeed close to a parity, not only can you get its value correct on most points, for all points you can get its value correct with high probability. Okay, so we'll use this sort of like a subroutine later when we're designing some other testing algorithms. Okay, now the danger zone. Oh, John. Unbelievable. Like the guy walks in the door just as I say that. Hey, John. How's it going? We're just having fun in here. Great. I'm okay so far, too.
Oh, cool. What happened? What did I miss?
It was good times. We'll have to catch you up later. Okay. So, so that was testing parities. And now, as I mentioned at the beginning of the class, what we really want to ultimately talk about today is testing, local testing, dictatorship. So this is the class D of all dictator functions. And in some ways, this is, one of the most important, if not the most important classes of functions to test, at least for this PCP hardness of approximation business. Okay, so it looks pretty simple. I mean, in fact, it's a subclass of the class of all parities. It's just n out of these 2 to the n functions. Although, unlike in learning, just because you can test a class does not necessarily mean you can easily test a subclass. So we actually have to be a little bit smarter to figure out how to test the class of all dictators. Okay, so what we need if we're going to try and design, let's say, a 2 or 3 or 4 or something query local tester for dictatorship, in particular, we need some kind of result that characterizes dictatorships. Some sort of theorem about a Boolean function f such that if you do this thing involving f, you get some result if and only if f is a dictatorship. Does anybody remember a result like that from lecture 4-ish? Any theorem where the conclusion is if and only if f is a dictator? Very good. Yeah, that's right, Brian. Arrow's theorem. Very good. Remember, in Arrow's theorem, it was about you have some Boolean function f, and you're using it to try to hold an election between 3 candidates, where you hold all the pairwise, 3 pairwise elections, using f as a binary voting scheme. And this had the unfortunate potential outcome that you could get an irrational result where somehow society prefers A to B and they prefer B to C, but somehow they also prefer C to A. And Arrow's theorem said that if you're using a Boolean function like f to hold such a three-way election, this always has a chance of happening unless f is a dictator, or the negation of a dictator, but close enough. So this suggests a nice, pleasant test that you might try to use to test the class of dictators. So we'll call this the not all equals test, NAE test. Remember, NAE is stands for not all equal. It's the predicate which is true if not all of the input bits are the same. And it just goes like this. Pick three strings, x, y, and z. These are like the votes in the three pairwise elections, from -1, 1 to the n, uniformly, but subject to the fact that for each coordinate, this is like for each voter, the three bits xi, yi, and zi are not all equal. Okay? These corresponded to the voters' preferences. They have 6 possible preferences, preference lists if there are 3 voters, 3 factorial, and there's 6 possible ways for 3 bits to be not all equal. Well, if you don't remember all this, it's not really that important. Okay, and then just query f on x, y, and z and accept if and only if the 3 results are not all equal. Okay, so this is a 3-query local tester that we might try to analyze to see how well it does as a tester for dictatorship. You can see right away that we're in good shape if the function is a dictator. It will definitely pass this test with probability 1. Also, it'll pass with probability 1 if f is an anti-dictator, which is not 100% what we are hoping for, but it's not too stressful. Well, let me remind you what we did with this test in terms of Fourier analysis. What we saw was the probability that, given a function f, that this test will accept. This is like the probability of getting a rational outcome in a 3-way election using f as the voting rule. It had this formula, 3/4 minus 3/4, the noise stability at -1/3 of f. It's not hard to prove if you write it all out. And expanding out the Fourier formula for this in terms of the weights, Fourier weights of f at differing degrees, you get 3/4 minus 3/4, the weight of f at degree 0, plus 1/4, the weight of f at degree 1, minus 1/12, the weight of f at degree 2, plus 1/36, the weight of f at degree 3, minus ... Okay, remember if you have a Boolean function, these weights add up to 1. Now, as I said, certainly if f is a dictator, you just write if f is in D, then the probability of acceptance is 1. You can also see this from the formula. All these weights are 0 except for the weight at level 1, which is 1. So you get 3/4 plus 1/4 is 1. And you can also kind of see from the formula that, if the probability of acceptance is near 1, I mean, if it's really, really close to 1, you must have almost all your weight at level 1, because otherwise you're not going to add up to close to 1. In particular, let me just quickly say, if the probability of acceptance is at least 1 minus epsilon, then that implies that the biggest this can ever be, this right-hand side can ever be, is 3/4 plus 1/4 times the weight at level 1, plus the next best thing is you have all your remaining weight at degree 3, so plus 1/36 times all the remaining weight. So if you accept this probability at least 1 minus epsilon, then this upper bound on your probability of acceptance has to be at least 1 minus epsilon. So if you just rearrange this, solve for the weight at level 1, you get that the weight at level 1 of f has to be at least 1 minus some constant, 4.5 times epsilon. Okay, this constant is not extremely important, but it's just quantifying what I said. The only way you can pass with probability really close to 1 is if almost all of your Fourier weight is at degree 1. Now, the conclusion we were kind of hoping for is that not just all your Fourier weight, almost all your Fourier weight is at degree 1, but that you're actually close to a dictator. Now, again, we don't quite, you could certainly be a negative dictator and have all your weight at level 1. So the best thing that you could hope for, potentially, is that this implies that you're O of epsilon close to, let's say, plus or minus a dictator. Okay. And this fact is actually true. It's a theorem called Freed-Gutt-Naur theorem, which we will prove today. So if you believe that theorem, then you immediately get that this test is a 3-query local tester for the class of dictators and negated dictators together. All right, with rejection rates, the reciprocal of 4.5. So that's, any questions about that, by the way? Okay, so that's neat, but it's not ideal. One, because of this thing, I wanted to test dictators, and I tested a slightly different class here. And second, because this FKN theorem is a little bit hard. I mean, we'll do it, but it's a bit of a pain. It would be more pleasant if we didn't have either of these problems. And in fact, there's a way to get rid of both these problems quite easily using things we already know. Can anybody suggest it?
You can really easily tell if you suspect that it's either a dictator or an anti-dictator. You can easily test which one it is by just throwing the 0 vector in there.
Okay. So the suggestion was, let's say you do this test. Let's say you're not too concerned about the fact that you use this painful theorem, FKN theorem. You're willing to take it. So now if you do this test, you're kind of convinced that the function is very close to either a dictator or a negated dictator. So Brian suggested at that point, you could say, let me do one more query. I'll just query it on the all 1 string. And if that's 1, I know it's a dictator. And if that's minus 1, I know it's an anti-dictator. There's a bit of a problem with that. Can somebody say what the problem is? They don't have to be random. But remember, after you've done this test, you're not convinced that it's equal to a dictator or to a negated dictator.
That could be one of the places where it's on.
Right. You know that it's close. Like maybe only it differs from a dictator and anti-dictator in a very small fraction of strings. But the all 1 string could be one of those strings where it differs. So you kind of really want to know the value of this guy that you're close to on the all 1 string, but you can't just query it. What can you do? Very good. You could local correct this. We had that little local correction algorithm. Oh, it's right here. See, at this point, sort of, if you pass with probability 1 minus epsilon, we know you're O of epsilon close to either a dictator or a negated dictator. So you could exactly run this algorithm, make 2 more queries where x is the all 1 string, and you get the result that tells you if you're a dictator or not with high probability. Yeah, so that will exactly work. That'll take 5 queries. Yeah, and that solves this one problem of the negated dictators. That's a perfectly good solution. I'll tell you another solution now. So we'll also illustrate a nice point. The other trick that you can do is just combine the NAE test and the BLR test. Okay, because among plus or minus dictators, only the plus dictators are also parities. Okay, Okay, the other guys are negated parodies. So here's a theorem that we'll prove. I'll prove this one kind of in full care, and then I'll stop being quite as careful with subsequent analyses. So here there is a 6-query local tester for D dictatorship class with, I don't know, rejection rate 0.1 or something. Okay. As I said, we really don't care too much about these rejection rates as long as they're absolute constants. Okay, and it's really just just do both these tests. We just say this is a. Okay, so let me do the proof of this. Okay, so if F really is a dictator, then this combined test will still pass with probability 1 because the two pieces both pass with probability 1. A dictator is, in particular, a parity. So the only thing we have to worry about is the opposite direction. Okay, so let epsilon be between 0 and 1. And suppose that the combined test is at least 1 minus epsilon. Sorry. It's at least 1 minus 0.1 epsilon. Okay, that's where the rejection rate goes in here. Our goal now is to show that F is epsilon close to some dictator. Okay, that's precisely what we need to do. Okay, well, let me call this statement star. If the overall test passes with probability at least 1 minus 0.1 epsilon, it's composed of two parts, then actually both of them have to pass with probability at least 1 minus 0.1 epsilon, right? If one of them rejected with probability 0.1 epsilon, then the overall test would reject with probability at least that much. Okay, so we know this implies that just the NAE test alone is at least 1 minus 0.1 epsilon, which by this fact right here implies that the weight at level 1, degree 1 of F is at least 1 minus, I don't know, 0.45 epsilon. As I said, you can see it's already starting to get slightly annoying to deal with these constants, so I'm going to eventually become more sloppy about it. But I'll do it correctly here. And we also know from this star that the BLR test also passes with probability at least 1 minus 0.1 epsilon, which implies there exists some S star such that F hat S star is at least 1 minus 0.2 epsilon. Okay, so conceptually now we're done. I mean, if you look at it, we know from the second thing that there's one giant Fourier coefficient that's practically 1. And we know from the first statement that the weight at level 1 is practically 1. So, I mean, it's got to be that that giant Fourier coefficient is itself at degree 1, okay, which completes the proof. So since I said I was going to be finicky, I'll just do it properly. If, for contradiction, this S star was not of degree 1, then the total weight of F which we know is 1, would be at least the weight at level 1, which is 1 minus 0.45 epsilon, plus the square of this number, because this weight is somewhere other than degree 1, 1 minus 0.2 epsilon squared, which is at least 1 minus 0.45 epsilon, plus 1 minus 0.4 epsilon, which is at least 2 minus 0.85 epsilon, which is strictly bigger than 1. Because epsilon is between 0 and 1. Okay, that's a contradiction. Okay, so therefore, S star has to actually equal 1. So we know that, let's say S star equals some set I. So therefore, by the second statement, we know that f hat I is at least 1 minus 0.2 epsilon, which actually means that f is 0.1 epsilon close to the dictator chi I. Which is actually even better than we needed. We only needed that it was epsilon close. But that's good too. Okay, any questions about that? All right, so that's cool. We did it. We tested the class of dictatorships, and even had the pleasant aspect that we didn't need this slightly painful FKN theorem. Now, you see this test has two parameters, the number of queries and the rejection rate. And as I said a few times, don't really care so much about this one. We do kind of care, though, about the number of queries. We're happier when it's smaller. I mean, 6 is small, but we want to go smaller. So actually, we can get this test down from 6 queries down to 3 queries. Does anybody, perhaps who's seen it before or not seen it before, know how to get down from 6 queries to 3 queries? Not quite, because in one test you want to have x plus y equals z, and the other ones they're like have these not all equal columns. But it's close to that. So I'll write a theorem like this. There exists a 3-query local tester for dictatorship with rejection rate 0.05. And the proof is just do this test. With probability 1/2, do the BLR test. Really? It's funny? I don't know. I thought it's a good idea. With probability 1/2, do the NAE test. OK, I call this the BLR plus NAE test. OK, so that always makes at most 3 queries. And let me just do the analysis, sketching it. Still, if you're a dictator, you pass with probability 1. And suppose, this is kind of like the proof sketch. Suppose this test accepts f with probability at least 1 minus 0.05 epsilon. Then I claim the BLR test accepts with probability at least 1 minus 0.1 epsilon, and the NAE test accepts with probability at least 1 minus 0.1 epsilon. Why is that? Well, I mean, if one of them rejected, let's say the BLR test rejected with probability at least 0.1 epsilon, you do it half the time. So overall, the test would reject with probability at least 0.05 epsilon. Okay, and similarly for the NAE test. OK, so then once you have these two statements, that's all we used over here. So it's the same rest of the proof. Yep?
You said at the beginning that once you pick your x's, the algorithm has to be deterministic to pick your.
Yeah, actually, I made a slight mistake when I said that, and I decided not to correct myself. But let me correct myself now. And we'll say this more clearly when we talk about CSPs. What you really need to do is the following. The algorithm uses its randomness right at the beginning to decide two things. A, what strings it's going to query, and B, what predicate it's going to use, what predicate it's going to apply to the outcomes to decide accept or reject. So actually, what the test really does here is, with probability 1/2, it chooses x, y, and like z equals x, y. And it chooses, like, I'm going to use the predicate f of x, or the check f of x, f of y, f of z equals 1. And then it's like, I've used up all my randomness. This is what I'm going to do. Go. And in this case, it chooses x, y, and z such that all the bits are not all equal. And it decides that it's going to test not all equal f of x, f of y, f of z. And then its randomness is done, and it says, this is what I'm going to do. Go. So it's slightly more than what I said, that like it uses its randomness to decide its strings, and then it's deterministic. It uses its randomness to decide what strings it's going to query and how it's going to go from the outcomes to its accept reject. It uses the randomness to decide that, and then it does that deterministically. That's an excellent point, actually. Okay.
Sorry, even if it, like, in the general case, all of this might be again a minor thing, but in the general case, if it can classify at the end,
Yeah.
Why can't it absorb this right in the beginning?
Yeah, I can. So you could let it.
Is that without loss of different?
Yeah. Yes. You're saying like it could use randomness to choose its strings, get them, and then use some, like, let's say, separate additional randomness, as long as it's not based on the outcomes, to decide maybe what predicate it's going to use. But then it could have done that before. Like, it shouldn't look at the outcome and then decide what predicate it's going to use to decide acceptance or rejecting. Acceptance and rejection. Rejectance? Yeah, that's what I blurted out there. Okay, so this is a cute trick, and let me just say that, you know, generalizing this trick, this is a little fact that you can remember. So with this trick, you know, you can combine a bunch of tests, basically some like R1 query through some RT query test into one test with the maximum of R1 through RT queries rather than the sum. Okay. You lose a little bit in that the rejection rate, this lambda goes down by a constant factor. It goes down by like t, I guess. But we don't care so much about that. We're much happier to be able to take the maximum query complexity of a bunch of subroutines rather than the sum of their query complexities. Okay, so I'm now going to take a little interlude. I mean, it's a little annoying that we're going to have to take this interlude. Because I want to keep telling you about testing dictators and why once you have a dictator test, you can use it to create all sorts of great tests, and you can use it to create probabilistically checkable proofs and hardness of approximation results and stuff like that. But interlude, I want to prove this FKN theorem to you, because if we don't do it now, then we'll never prove it. But it's a good theorem to prove. And it's also like the nicest first application of hypercontractivity, which we saw last time. So now is the best time in the course to prove this theorem. So don't forget all this testing stuff, but let's make an interlude. OK, so this is the theorem we want to prove. This is changing topics. If you have a Boolean function and it has 1 minus epsilon of its weight at degree 1, then it's O of epsilon close to plus or minus a dictator. There are several proofs of this theorem, and the one I will present to you now is not the most, I don't find it the most intuitive, but it's the shortest. So we'll do it. And it's an application of hypercontractivity, which is nice. Study it. If you come up with like an excellent intuition for it, tell me, because I would like to know. But other than that, I can just say the proof is relatively short. OK, so let me start with a lemma. Cast your mind back 1 week ago. We talked about reasonable random variables. Remember, these are random variables that have the property that their fourth moment is not much bigger than the square of their second moment. And I told you that such random variables have lots of nice properties. And one of those properties was some kind of anti-concentration. Okay? In fact, this was one of the problems on your homework, maybe 1B or something, some other part B statement. And furthermore, last time, our main theorem was this Bonami lemma, which said if you have a low-degree polynomial of bits, then it is reasonable, where the level of reasonableness was some constant 9 to the power of the degree. So you can put those two lemma statements together and deduce that if you have a low-degree polynomial, it's not too concentrated around its mean. Okay? And so that's what this lemma will do. This is a nice lemma to know. So here it is. Let g be a real-valued Boolean function of degree at most k. And you can think of g of x as a random variable, a 9 to the k reasonable random variable. And it has some mean, which we'll call mu. And it has some variance. Well, let's say it has some standard deviation, which we'll call sigma. And let's assume this is non-zero, so it's not a constant. And let's let h be the function that just shifts things around so it has mean 0 and variance 1. Okay, so we'll look at g minus mu times 1 over sigma. Okay, mu and sigma are just constants now, so this is a mean 0, variance 1 function. Actually, I'm going to prove the lemma and state it at the same time. So of course we know that the degree of h, well, I just took h, subtracted a constant, and multiplied by a constant, so it doesn't change the degree, is also at most k. Which means, by Bonami's lemma, that the random variable, if you think of x as random string, h of x is 9 to the k reasonable. Okay, so as I said, you have that anti-concentration statement on your homework. If you remember it very well, which I hope you do, by the homework, taking this parameter t to be a half, we get that the probability over random x that h of x is at least t, or in this case, a half, times the 2 norm of h, which is 1, because we normalized it to have mean 0 and variance 1, was at least, well, it was at least 1 minus t squared squared times 9 to the k, 9 to the minus k. So it's like 1 minus half squared squared times 1 over 9 to the k, which is, I guess, 1/16 9 to the 1 minus k. And let's just remember what h is. It's g minus the mean over sigma. So if I just rearrange the event inside the probability, I conclude, let me write it over here, g, degree of g at most k implies a probability over x that g of x is at least half a standard deviation away from its mean, is at least a constant. It goes down exponentially with k. Okay, but this is still pleasant. I mean, if you just have any old random variable, it might be like super concentrated around its mean. But this actually tells you that, you know, if you're reasonable, you cannot be super concentrated around your mean. Any questions about that? Okay. Okay, so now on to the somewhat opaque proof of the FKN theorem. Okay, so the FKN theorem says, like, the hypothesis is that the weight at level 1, degree 1, is practically 1. Okay, and we want to show that means you have to practically be a constant, a plus or minus dictator. Okay, so so the hypothesis is that the weight at degree 1 of f is, let's say, 1 minus delta, where delta is small. And we're trying to show that f is close to plus or minus a dictator. So what we'll do is let L be the linear part of f. Yeah, and our goal will really to be, well, I don't have that much intuition. I'll just get to it. So we'll apply the lemma with G equal to the square of the linear part. Okay, so what is the square of the linear part? If I square this, what do I get? I'll get the sum of f hat I squared, xi squared, but xi is constantly 1, so that's just times 1. Plus, then I'll get the cross term, sum over I not equal to j of f hat I, f hat j, xi xj. Okay, and this thing is just by hypothesis, that is the weight at level 1, so that's 1 minus delta. Okay, so this is the Fourier expansion of L squared. It's 1 minus delta plus this degree 2 stuff. I'm solving unordered pairs here. Okay. So since we're going to apply the lemma, let's figure out what mu and sigma are. So what is the mean of L squared? Can somebody tell me? Yeah, 1 minus delta. There's the Fourier expansion. It's just the empty Fourier coefficient. And the variance can somebody tell me what that is? If you have any Boolean function and you're staring at its Fourier expansion, its variance is equal to this is lecture 1. Sum of the squares of the non-empty Fourier coefficients. So it's the sum of these things squared. So sum over I does not equal j of f hat I squared, f hat j squared. All right. Okay, let me continue. Let me just manipulate that slightly. Because this is almost the square of the sum of the squares of the f hat i's. You see, it's sum over I of f hat I squared, but then we counted the non-cross terms too many times. So you need to subtract off sum of f hat I to 4th. Okay, and again, this is 1 minus delta, the sum of f hat I squared. It's by hypothesis, so this is 1 minus delta squared minus sum of the 4th powers of the degree 1 Fourier coefficients. And this is nice because this is always an excellent proxy for like the maximum of the degree 1 Fourier coefficients. By this trick of like taking out some copies and maxing over them and using Parseval on the rest. Okay, so this quantity is large if and only if one of the degree 1 Fourier coefficients is large. And in particular, the whole point of the proof is once we apply this anti-concentration lemma to L squared, what we're going to deduce is that this variance is actually very small. So we'll show that this sigma squared, the variance, is at most O of delta. And that will complete the proof. So why? So what we get is that O of delta is equal to, this is like 1 minus 2 delta-ish minus this. So therefore, we get that the sum over I of f hat I to the fourth is at least 1 minus O of delta, plus 2 delta, if you will. I can say this is at least 1 minus 2 delta plus. Okay, so just rearranging that, the O of delta goes up by plus 2 delta. And now we see this favorite trick of ours. This is at most the max over I of f hat I squared times the sum over I of f hat I squared. This is at most 1 by Parseval. Okay, so therefore what we've shown is the maximum Fourier coefficient of degree 1 squared is at least 1 minus O of delta, which implies there exists I such that f hat I squared is at least 1 minus O of delta. F hat I in absolute value is at least 1 minus O of delta. That's f is delta close to the dictator, well, to plus or minus chi I. So the only thing, this is what we need to do to finish the proof. Any question? Okay, so let's just do it. Somehow this part is intuitive. If like the degree 1 part has tiny variance, no, if the degree 1 part squared has tiny variance, it's like it's constant. And its mean is like practically 1. So you have like an essentially constant random variable, which is mean is 1. It means basically it has to be Boolean valued, the linear part already. Okay. All right, so we apply the lemma to L squared, which has degree 2. Okay, and we just immediately, just writing it in, we get that the probability over x that L squared of x minus its mean, which we know is 1 minus delta, probability that's greater than or equal to the square root of the variance, sorry, half the square root of the variance of L squared, is at least 1 over 16 over 9, which is 1 over 144. Okay, so you see what's going on here. Suppose for contradiction that this is false. Okay, so suppose for contradiction that this variance L squared is at least like 10,000 delta. Okay, just to be safe. Okay, by the way, just to make sure you're following. Now, once we get a contradiction, the whole proof is done, right? Because this proves that the variance is indeed at most O of delta. Okay, so having made the supposition, last step is let's get a contradiction. So let's just think it over. There's like a little bit of calculation, but it's going to be cool. So, and what are we eventually going to contradict, by the way? We're going to contradict this. Okay, so the variance supposedly is at least 10,000 delta. So this thing here is like, this thing is at least square root is like 100 root delta, so it's at least 50 root delta. Okay, so what this is saying is when you pick a random x, there's like quite a reasonable chance that L of x squared is quite far from 1 minus delta. Okay, this minus delta is like quite negligible compared to this 50 root delta. Right, so we can just say that, like, let's rewrite this slightly. That implies that the probability that L squared of x minus 1 is at least, say for safety, 49 root delta. Delta is smaller than root delta is at least 1 over 144. Okay, so when you pick x at random, there's quite a decent chance that L squared is quite far from 1. In particular, L in absolute value is quite far from 1. So L of x, therefore, when this happens, has to be quite far from f of x. Right? Because f of x is plus or minus 1. So if L squared is far from 1, then L squared is far from f of x squared. So the remark is, well, I mean, how shall I write this? Well, L of x is far from 1, then L of x is far from f of x, because f is plus or minus 1 valued. In particular, if you just calculate now, whenever this event occurs, let's say if L squared minus 1 is bigger than 49 root delta, that means that, I don't know, absolute value of L minus 1 is at least half of this, basically. So I'll say 15 root delta to be safe, which in particular means that L of x minus f of x is at least this much in absolute value. So its square is at least the square of this. So let me just write 200 delta to be safe again. Okay? Don't get overly excited about these calculations. Just L squared is far from 1, then L minus f has to be at least basically the square of that. Is that OK? So now we're done, because, see now, in that case, this immediately tells us, if I look at the expected value over x of L of x minus f of x squared, I know that at least 1 over 144 of the time, it's at least 200 delta, which is bigger than delta. But this, I mean, I've just subtracted the linear part of f from f. So this is exactly the sum over k does not equal 1 of the weight at level k of f, which is supposedly delta, because it's the weight at level 1 is 1 minus delta. So that's the contradiction. OK, so does anybody know what just happened there? This is one of the proofs of the Friedge-Collide-Noether theorem. I don't know. Basically, somehow you just use the fact that f squared is 1, and if f is practically the same as its linear part, then its linear part is reasonable since it's degree 1, and some calculations work out. OK, that's the end of the interlude. So let's go back to property testing. OK, so the last thing I'll do in the class today is tell you why we were so keen on testing dictators. So you know, the first local testing algorithm we saw was the BLR test. It was quite simple. It tested the class of all parities. Then I said, let's test the class of all dictators, which is a subclass. And I pointed out that, you know, just because you're testing a subclass doesn't mean things are easier. In fact, it was harder. I mean, we had to use more smarts to come up with a testing algorithm for dictatorship. But we did. Without even using this FKN theorem, we gave a 3-query local tester for dictatorship. And what is so cool about that is once you have that, then you can actually get a testing algorithm for any subclass of dictatorship at all. Anyone. So that's kind of somewhat remarkable, actually. Here's the theorem. Let script S be any subset of the class of dictators at all. So i.e., S is the set of all functions chi I, a dictator, such that I is in some set S, where S is some completely arbitrary subset of N. Okay? you fix some totally arbitrary subset of 1 through n. It can be anything. And then you can test whether a function is a dictator where the dictator bit is in that set S. So then there exists a 3-query local tester for script S. Okay, with the rejection rate, if you must know, I have to look it up, 0.05, I think, 0.01. Okay, and this is kind of amazing. The fact that it's, in a way, the fact that it works for all arbitrary sets is going to be the driver behind some cool things that we do in terms of probabilistically checkable proofs. And the fact that we can do it for all sets, you'll see, comes from the fact that we can test dictatorship. OK, so here's the proof sketch. As I said, this is where I'm going to start to get slightly lazy about being super careful about arranging the rejection rate ahead of time. I think you'll be convinced by this sketch. So it's going to be a testing algorithm with like a few subroutines. So what's the first subroutine that we should do if we're trying to test that F is a dictator from the set S? Very good. Yeah. So first, first do the 3-query BLR plus NAE test. OK. And we're only going to do tests, by the way, that pass with probability 1 if the function is a dictator from the set S. So the easy part of the definition will always be easy.
So wait, but we already used our 3 queries.
Aha, that's right. So what can you tell me then?
Oh, that's it.
No, that's not it.
Well, so, I mean, we could do some other test, but then do that trick where we...
Right. We're going to do some more subroutines, each of which uses no more than 3 queries. And then I'm going to say at the end, like, now combine them with that trick that lets us take the max of the query complexity rather than the sum. Yeah, good point. It's a proof sketch. Good. So the main thing we need to do in the proof sketch is, say that if this thing passes with probability 1 minus epsilon, then if f, an arbitrary function, passes the test with probability 1 minus epsilon, then it's epsilon close, or O of epsilon close to being in this set script S. So if this passes with probability, or is accepted, it's probability at least 1 minus epsilon, we know that f is O of epsilon close to some dictator. It's like chi I star. Okay, we don't know what I star is, but we do know that f is close to some dictator, chi I star. So now the next thing we kind of have to do is check, well, that this I star is in this set capital S. Okay, if we could do that, then we'd be done. So does somebody have a suggestion on how to do that? Yeah.
Can you take the string that's 1 on S and negative 1 not on S and apply that noise thing to it?
Yeah, perfect. Marla got it exactly right. Yeah, so we need to now understand if I star is in S. So as Marla said, let me let 1S be the string in minus 1, 1 to the n, which is the indicator of the set S. Okay, well, so it just has a 1 in the ith coordinate if I is in S, and a minus 1 if it's not in S. And now what we really want to know is, this is like an aside, we really want to know chi I star of 1S. Okay, because if this was 1, then I star is in S, and if it's minus 1, it's not. So we cannot just query like f on this string, but this is exactly the issue we talked about with Brian before. We're almost there. We just do local correction of f on this string 1s. Okay, so remember this local correction algorithm. This is two queries. And the theorem is that if the function f is epsilon close, or O of epsilon close to some parity, which at this point we know it is. It's not just close to a parity, it's close to a parity of cardinality 1. That's good. Then for every string here, your favorite string, this will give the correct answer, namely this, with probability 1 minus 2 epsilon. Maybe 1 minus O of epsilon in this case. OK, so the algorithm will be do local correct, and then except if and only if the output, I mean the answer is 1. And basically this works. So if these two tests together pass with probability 1 minus epsilon, then when we use the trick to combine them, have a 3-query test overall, we know that like both components pass with probability 1 minus O of epsilon. So f is close to this guy. And this answer is, except with probability O of epsilon, equal to the true answer, which exactly tells us if I star is in S or not. So without writing all those words, indeed, the overall test passes with probability 1 minus epsilon, implies that f is O of epsilon close to chi I star for I star in S. That's the end of the proof sketch. Any questions about that? OK, so that was pretty cool. That shows that well, we can test any subset of dictatorship. Now, the thing we're going to talk about next time is whether you can test any property at all. And it's actually very easy to check that there are plenty of properties that you cannot test with like 3 queries or n queries or any small number of queries. But what we'll show next time is that if you're allowed to get a proof, somebody's allowed to give you not just black box access to a function, but black box access to a supposed proof that the function has the property, then you can test any property whatsoever with 3 queries. And it just uses this theorem and a few extra tricks. So we'll see that on Monday, and see you then.